Alright, now let's talk about the vestibular system. So this is the system that detects mainly your position, the position of your head in space, and the movement of your head as well. And so it does that by using this organ, or this group of organs, called the vestibular labyrinth. You have one set of these structures in each ear, and so this is how they're kind of oriented next to the cochlea. So remember, the cochlea is the organ for hearing in the auditory system, but it is right next to the vestibular labyrinth. In fact, they're connected to each other. So the fluid that fills the cochlea also fills the chambers of the vestibular labyrinth. And there are basically two sets of structures in here that are important. These semicircular canals, which are pretty much what they sound like. There's three of these in each ear. They're responsible for detecting angular rotation of the head. And then these two little chambers called the otolith organs, which mostly detect linear motion, but also they are responsible for your ability to detect the direction of gravity. So first, we'll talk about the otolith organs. Again, there's two of these chambers in each ear, and they're called respectively the utricle and the saccule. So you have a left utricle and right utricle, and then a left saccule and a right saccule. And each one is actually two chambers that's divided down the middle or somewhere inside by a membrane called a macula. And the macula acts kind of like the orbital corti in the cochlea. So it's just a membrane that contains hair cells. And the hair cells have cilia that are activated or depolarized when they're deflected, just like the hair cells of the cochlea. The utricle contains a macula that is more or less horizontal if you're standing straight up with your head facing forward. And then the saccule, each saccule contains a vertical macula. So in other words, the macula is more or less vertical if you're standing straight up with your head facing forward. The cilia, the stereocilia of each one of these hair cells is embedded in a layer of gelatinous material which is secreted by these supporting cells that surround the hair cells. And so this gelatinous material covers the cilia, and the cilia are embedded in it. And so when it moves, the cilia move with it. And then covering the gelatinous cap are these little crystals of calcium carbonate that are called otoliths. So these are not cells. This is basically just a little tiny crystals that are secreted by or that precipitate essentially onto the surface of the gelatinous cap. And they're called otoliths because that's what they are. Otto means ear, and lith means stone. So literally the word means ear stone or ear rock. And their job is just to sit on top of this gelatinous cap and just sort of provide weight. Because if you tilt your head in any direction, then gravity will pull those otoliths down, and when they do, they will the otoliths will cause the gelatinous cap to shift in that direction, and that pushes the stereocilia in that area in the same direction, which will, for some of them, will cause deflection, and that then activates they then release a neurotransmitter which causes these axons, which are connected to this structure up here called Scarpa's ganglia. So Scarpa's ganglia is basically the output structure for both the otoliths and the semicircular canals. So again, the job of the otolith is to, in this case, if you're standing still anyway, to essentially detect which way is down. Because each one has a macula covered in hair cells, and those hair cells have cilia that are oriented in every possible direction. So up here, this is one of the horizontal macula, one of the utricular maculas, and these arrows represent the direction of depolarization for each set of hair cells. So all along the surface, there are hair cells with cilia that are oriented in the directions indicated by the arrows, which means that no matter which way you tilt your head, some of those stereocilia will be deflected, and so whichever ones are deflected tell your brain which way down is. So, and the same thing goes for the saccular macula. They're oriented horizontally and vertically, and so at any given moment, at least one of them will be, some subset of them will be pulled in the direction of gravity. So in other words, most of the time when you're just sitting or standing upright, these cells down here on this part of the saccular macula will be deflected because that's the way gravity is pointing. And so that tells your brain that gravity is down. If you were to, say, lean your head forward so that these hair cells over here, their cilia were deflected because this now becomes the direction of gravity, then those cells would send a signal to your brain saying that that direction is down. So again, this is really important, obviously, for your sense of balance and just the sense of where your head is in space. And so if any of these are malfunctioning, this is not a sensory system, and this goes for the vestibular system overall. This is not a system that you're normally consciously aware of unless something goes wrong with it. So if there's some sort of malfunction with the vestibular system, that creates a sense of imbalance or dizziness, or sometimes what's called vertigo. Now the other thing that the otolith organs detect is linear acceleration. So that means that anytime your head is pushed in any direction, the stereocilia that correspond to that direction of motion will be deflected in the opposite direction simply because of inertia. So in other words, let's say you are sitting in a car and suddenly the car starts accelerating forward, your head will start moving forward, but the otoliths would be sort of pulled backwards. So it would be almost as if gravity was pointing back away from, or toward the back of your head, because these hair cells right here and also these hair cells right here would be deflected. And that would again tell your brain that there is a force that's pushing your body forward. And then vice versa if you were suddenly pushed backwards or in any direction. But importantly, that only works for linear acceleration. So constant linear motion, meaning that there's no acceleration, would not activate any of these hair cells because they would be moving at the same speed, hopefully, as the rest of your head. And so they would report to your brain that there is no motion, and they would just go back to reporting the direction of gravity. So that's why that you get that feeling of motion when you say are in a car that's speeding up or slowing down, but you don't get that feeling of motion once the car or whatever you're in is at a constant velocity. So the semicircular canals work in a similar way, except that they detect angular acceleration. And so the semicircular canals are exactly what they sound like. There's 3 of them in each ear, on each side of the head, and the semicircles that they get their name from are situated roughly 90 degrees to each other. So if you look down on the top of the head, you can see that the 2 of the semicircular canals in any given orientation look like they're at basically 90 degrees to one another, which means that they can detect motion in all 3 planes. So sort of rotating front to back, rotating left to right, and rotating side to side. If you were in an airplane, this front to back motion you'd call pitch, the side to side motion would be yaw, and left to right would be roll. And so this is detected by more hair cells that are in the base of the semicircular canal. So the base of each canal, has this little bulge called an ampulla. So this is the ampulla of one of the semicircular canals. You can see the ampulla in the base of these canals down here. And again, the hair cells have cilia that are embedded in a gelatinous cap, except this time, instead of being a flat surface like in the otolith organs, the gelatinous cap forms a little mushroom shape. And same thing, deflection of that cap, what here it's called a cupula, in either direction will deflect some of the hair cells, the stereocilia of some of the hair cells, which will depolarize them and cause them to send a signal down these vestibular axons. Which direction they move depends on the movement of the fluid inside the semicircular canal. So when you're not moving, when your head is not rotating, this fluid, called endolymph, is basically still. In other words, the cupula is not moving either direction. But if, and let's say we're looking in the, would be in the one of the horizontal semicircular canals here. So if you rotate your head to the left, actually you're specifically looking at the horizontal semicircular canal on the left side of the head. So that means probably this one right here. So when you rotate your head to the left like this, so your head's rotating to the left, the fluid inside the semicircular canal moves in the opposite direction. And that's just because of inertia. As you accelerate your head to turn clockwise, the endolymph essentially flows because it hasn't yet caught up to the movement of your head in the opposite direction. So that flow will push those the cupula and thus the cilia inside counterclockwise. And of course, the opposite would happen if you rotated your head to the right. The endolymph would be pushed to the left or clockwise, and it would push the cilia that way. So again, the stereocilia move because they're stuck inside that gelatinous cupula, and any angular acceleration, meaning changing the rotational velocity of your head, will cause some of the stereocilia in at least one set of semicircular canals to rotate. So depending on what direction you're rotating, you'll be activating a different combination of semicircular canals. Whether or not a given hair cell responds actually depends on the direction of rotation. So here we're measuring the firing rate, meaning the number of action potentials per second, from one of these vestibular axons, and during the rotation of the head. So up here, this is a graph showing the rotation speed of this person's head. They're rotating to the left, to the left, and then same thing down here. And this is showing the firing rate of hair cells or vestibular axons on the left side of the head, and this is on the right side of the head. And what you can see is that when they start rotating, so the rotational speed goes from 0 to some other value greater than 0, so they've started rotating. The semicircular canals on the left, or their hair cells, are activated, so they start firing action potentials. Meanwhile, on the right side of the head down here, these neurons actually fire less. So one thing that's important is that these cells, these neurons anyway, have kind of a baseline firing rate. So they, even when you're standing still, they're still firing at a baseline rate. So that in this case, when you rotate to the left, that increases the firing rate of the neurons on the left, but it decreases the firing rate on the neurons on the right. So that motion, because and this of course only applies to left to right motion or side to side motion. It doesn't apply to front to back motion because those semicircular canals should usually be moving in the same direction. But in any case, it's the direction of motion that determines whether or not they are activated. So for the horizontal semicircular canals, rotating the head to the left activates the left semicircular canal hair cells, and it inhibits the right semicircular canal hair cells, and vice versa. This also shows that the only thing that activates these is acceleration, or angular acceleration. So the firing rate only increases during this brief phase here, where you're seeing a short window of time where the rotational velocity is increasing, and then as soon as it becomes constant, so now here we're at constant rotational speed, the firing rate starts to go down. And in fact, it reaches baseline. And this is because, again, you're not accelerating anymore. You're still rotating. So in other words, the head is still rotating. So this person is just spinning in circles, going to the left. But because the rate of rotation isn't changing, the hair cells, basically what happens is the fluid inside the semicircular canal kind of catches up with the movement of the rest of the semicircular, or with the rest of the canal, and it stops pushing on those hair cells. So that's why you see the firing rate drop, because basically from the point of view of this semicircular canal, and this one, by the way, of course, it's also doing the same thing, it drops its firing rate during that acceleration period, and then it starts to return to baseline. So they're both basically telling the brain that during this phase, the head has begun to rotate to the left. And then during this phase, it has stopped rotating, or in other words, the acceleration on the head has stopped. Now, this is an important example of where your sensory systems can effectively lie to you, because during this phase, your head is still rotating, but your semicircular canals are sending the exact same signal they were when your head was still. So in other words, semicircular canals cannot tell the difference between this situation where your rotational speed is 0 and this situation where your rotational speed is some number greater than 0. All they can do is detect this situation where the rotational speed is increasing or decreasing, because then when you stop rotating, when the head stops rotating, your rotational speed goes down sharply. So you go from some number down to 0, and when that happens, the left semicircular canals start to drop their firing rate, and then the right semicircular canals do the opposite. They start to increase their firing rate as soon as your head stops rotating. So again, this is some misinformation from your sensory systems, because here your left semicircular canal has dropped its firing rate, and that's a signal from, you can see this from the right semicircular canal. A drop in firing rate means that the head is rotating in the opposite direction. So this signal is a signal to the brain from the semicircular canal that your head is actually rotating now to the right. And in fact, the right semicircular canal is saying the same thing, because the right semicircular canal is acting the way the left semicircular canal was when you were rotating to the left. So now both the left and right semicircular canals are sending a signal that says not only are you rotating, but now you're rotating in the opposite direction that you were a minute ago. So this effect is essentially why you feel dizzy after you spin around in a circle. During this phase, your brain is correctly hearing from the semicircular canals that you're increasing rotational velocity. But during this phase, it is incorrectly getting the impression that you have stopped rotating. And in fact, it would continue to tell you you're not rotating during this phase. But when you stop rotating, when your head stops spinning, then the semicircular canals send a signal to the brain that not only are you now spinning, but you've suddenly started spinning in the opposite direction. So now this semicircular canal is saying now the head is rotating to the right, and this semicircular canal is saying the same thing. And that miscommunication, or that mismatch between what your vestibular system is telling your brain versus what is reality. And of course, you have other ways of telling whether or not you're moving. You can see with your eyes, and you can feel with your somatosensory system where you are and where your body is. So that mismatch is what creates that sense of dizziness or vertigo. And same thing happens if, again, there's some sort of malfunction with these semicircular canals. So, for example, one of the effects of some types of inner ear infections is to cause one or both sides of the vestibular system to fill with fluid, malfunction, and that can create dizziness and balance problems for some people. And like I said, that's just pointing out that the only thing that really activates this system is acceleration, not constant rotation. So the central vestibular system is relatively simple. Again, this is not a sensory system that you, for the most part, have conscious access to unless something goes wrong. So there is no vestibular cortex per se, but there are various parts of the brain that get input from the vestibular system that are mostly involved in movement. So the axons from Scarpa's ganglia form part of cranial nerve 8, and those axons go into the vestibular nucleus, which is part of the hindbrain. There's a lateral and a vestibular section to the vestibular nucleus. And there's also a projection from the cranial nerve 8 directly to the cerebellum, but there's also a projection from the lateral vestibular nucleus to the cerebellum. We'll talk about the cerebellum more later because it's important in controlling certain types of movement. There's a projection from the lateral vestibular nucleus directly to the limb motor neurons and to the neck motor neurons. These are the neurons that control the muscles of your limbs, meaning your arms and legs, and your neck. And it makes sense that the vestibular system would communicate with those motor neurons, because if you are suddenly off balance or need to stabilize your body because of some it's rotating or moving in a way you didn't mean for it to, then you would use your limbs and the movement of your head to try to reestablish balance. There is a projection from the medial vestibular nucleus to the thalamus, which is probably the way in which you do have some conscious access to the sensory system, but again, you don't really aren't aware of it on the same level as you would be, say, the auditory or the visual systems. And then there is a projection from the medial vestibular nucleus to the extraocular motor neurons, and that's important because one of the functions of the vestibular system is to help control the eye muscles. You might wonder why you need the vestibular system to control the eye muscles, and mostly it's because of this thing. It's called the oculomotor reflex. And so this is a reflex, and we'll talk about reflexes more later, but generally it refers to any circuit where you have a connection between a sensory system, so in this case it'd be the semicircular canals, and some sort of motor response. And in this case, it would be the movement of the eyes. That's what oculomotor means. Oculo meaning having to do with the eyes, motor meaning motion. So this reflex is pretty easy to demonstrate. You probably use it all the time without knowing it. Basically, your eyes are always facing whatever you're looking at. So if you look out at anything in your visual field and fixate your eyes on that position, if you turn your head any direction, you will notice that your eyes always face the same way. So if I rotate my head to the left, it causes my eyes to rotate the opposite direction so that they're still facing the same way. Same thing if I look up and down. If I rotate my head up, my eyes rotate down so that they're still pointing straight ahead. So this is an important reflex because it helps kind of maintain the constancy or the illusion of constancy of the image hitting your retina. Otherwise, as you rotate your head, you would also have to rotate your eyes, and it's just easier for your visual system to process information if you are keeping your eyes pointing the same way. So this is just an example of the kind of reflex that the vestibular system is important for. The exact details aren't super important right now, but it's just an interesting example of what the brain can do with this information. So in this case, the head is moving to the left, so you're rotating the head to the left, and so what should happen is that the eyes should move to the right. So the muscles that move the eyes side to side are called the rectus muscles. So each eye has a lateral rectus muscle and a medial rectus muscle, and that's true for both eyes. So if you want to move your eyes to the right, you would want to contract the lateral rectus muscles and relax. If you want to move your eyes to the right, you would want to contract the right lateral rectus muscle and the left medial rectus muscle, because that will cause this motion. And meanwhile, you want to relax the right medial rectus muscle and relax the left lateral rectus muscle. And then vice versa if you want to rotate the eyes to the left. So the way the semicircular canals control this is that motion, the rotation of the head to the left, activates the hair cells in the left semicircular canal, which in turn activate neurons in the left vestibular nucleus. The left vestibular nucleus then has neurons that go to several different places. Their axons cross over to the opposite side of the brainstem and activate motor neurons in the left abducens nucleus. So this is the this is the right abducens nucleus. So this is information coming from the left vestibular nucleus to the right abducens nucleus. And then axons coming out of and this is an excitatory signal. So this pathway activation of the left horizontal semicircular canals activates the neurons in the right abducens nucleus. It's called the abducens nucleus because the axons coming out of it, they go to the eye, form part of the abducens nerve, which is cranial nerve 6. And so these nerves these neurons directly activate the muscles of the right lateral rectus muscle. So that contraction pulls the eye this way towards the right. Meanwhile, these neurons also have a projection that the left abducens nucleus has an axon that goes back to the left side of the brain and stimulates neurons in the left oculomotor nucleus. So the oculomotor nucleus contains the motor neurons that have axons that form the cranial nerve 3 or the oculomotor nerve. So when those are activated by the right abducens nucleus, that causes these neurons to stimulate the the medial rectus muscle of the left eye. And again, that motion, contracting that muscle, will cause the left eye to rotate to the right. Meanwhile, on back on the left side, the left vestibular nucleus also has a projection to the left oculomotor nucleus that's excitatory, and that causes the same thing as the projection from the right abducens nucleus. So the left oculomotor nucleus gets two excitatory inputs, one from the vestibular nucleus on the left-hand side, one from the abducens nucleus on the right-hand side, but the effect is the same. It increases the contraction of this left medial rectus muscle. Meanwhile, the left vestibular nucleus also has an inhibitory output, so it actually has an inhibitory effect on the left abducens nucleus. So these same axons branch, some of them are excitatory. If they're on the right side, they're inhibitory when they reach the left side. Again, what matters is the receptor expressed by these neurons. But in any case, inhibiting these neurons prevents these muscles from activating. And then there's a mirror image of this pathway from the left side. So these left abducens nucleus neurons have a projection to the right oculomotor nucleus neurons, but that pathway is basically taken away by this inhibitory signal from the left side. So it looks kind of complicated, but it's a relatively simple reflex. Again, all it does is it just keeps your eyes positioned in the same direction no matter what way you move your head. And this is a relatively simple reflex in the sense that it doesn't require any real input from the brain at all. In fact, it's very difficult to consciously inhibit this reflex. So it's hard, if you rotate your head, it's hard not to keep them fixated on a point in space. They have this tendency to try to sort of catch up with or prevent themselves from catching up with your head. And again, we'll talk about more examples of reflexes later on. But that is it for this chapter. So thanks for listening.